All right, so let's get started. Welcome back to CS596. And in today's lecture, we're gonna uh, go through the methods, techniques to evaluate machine learning models. All right, and this is the outline of the lecture today. So first, we're gonna uh, talk about how we split the data sets. Okay, we need to have different parts of the data sets and let the different parts play different roles. Okay, so through the previous two assignments, first of all, the linear regression, and in last week, we also released the logistic regression. And we use the term training data set a lot, right? A data set, the data points in the training set are used to tune the model's parameters. Okay, and that is, I would say, the core function of the data sets, or the key roles that a data set played in a whole machine learning pipeline, a machine learning process. But I think we mentioned a bit about testing. Yeah, we used the residuals, the mean square errors, to kind of evaluate how well a model is. And also, we use the index of how many correct predictions that the model being trained has made. Okay, but so far we didn't systematically talk about the usual practice or the regular practice of dividing the data set into training part, testing part, and we will introduce the validation part as well. Okay, and as we are using bigger and bigger data sets for machine learning, these kind of splits is more and more important because the data basically define the behavior of models. And if we want a model to have some general prediction power, or it has general good performance within a larger context, then the way we set up the data, including the training data and the validation data and the testing data, will be critical. All right. So after data, we're gonna introduce a bunch of computational metrics for evaluating the performance of models, right? We'll use one slide for regression model and a bunch of slides for the classification model. So basically, I would say in most cases, supervised machine learning model deals with classification problems rather than regression models. So our main focus will be on the performance metrics on the classification models. And lastly, we'll talk about overfitting and the ways to deal with overfitting. All right, so let's get started. So first, the splits of train developments or validation. So here the term dev set or development set is the same as the validation set. Okay, so we need to choose the splits or choose the proportions or ratios of splits carefully in order to make the model perform well, right? So a usual way is that the majority of the data okay, will be used as the training sets or the training data, okay, indicated by the blue color. And the dev sets or the validation sets is pretty much the smallest the proportion among the whole data sets. Okay, it is used as a holdout parts during the process of training. So these dev sets or validation sets, this small piece of data, will be periodically used during the training. Okay, it is not necessarily that within each iteration of the training loop we need to call the validation or call the development sets once, but we basically need to use that validation sets every like fixed number of loops, training loops. Okay, and the test sets is not that frequently used, but it is often used as a data sets that helps you comes up with a final report, or it helps you to gain some conclusion on how well this model you just trained perform. Okay, these test sets is not periodically referred to during the training process, but it is used at the final step, at the last step, when you want to write a report or you want to gain some conclusions about your model. You need to just use that data set, use that test set for once. Okay. So that's the workflow summarizes basically what I just described. We need to train the model, keep training the model on the training sets. And during the training, we use the dev sets or the validation set to see which model performs best or which parameters performs best. Okay, so that dev set is periodically used, and then evaluates. The final evaluation of the model will be applied upon the test set, so that we want to get an unbiased estimate. Okay, so the key numbers for the proportions of the splits is actually kind of depend on the size of your data. So if you have rather small data sets, say 100, 1,000, or 10,000, if you have a below 100,000 data sets, then data points, then we probably can use a split like 70% as training. And in this example here, we didn't even include the validation sets. Okay, so that is because to small data sets, the training process itself doesn't take a long time. Okay, the model can easily converge on the small data sets on especially when your model when the model is a simple model. Okay, so in that case, validation data set is not like a mandatory, but it's also up to you to decide whether you consider the data sets a big data or small data. So if you think validation data set is kind of needed because your model is big, or you want to observe how the training goes with respect to the validation performance, then it's okay if you like set 20% on data. So these are all very empirical numbers. And in the case for larger data sets, or so-called big data sets, say we've got millions of data points, then probably we can kind of split the data sets by assigning a very small proportion as validation and test. Okay, that is because when the data is big, the model is also big, and the time you need to spend for each evaluation loop or for each evaluation iteration is also expensive. It also costs you time and the computation power. So that's why it doesn't necessarily, it's not necessary to have that large validation sets or testing sets. So even people can use even lower proportions. So these are also very empirical numbers, basically from the decided by the size of your actual data sets. Okay, so I've got a question. After the depth sets, is that outcome used again on training data in some cases? Is that outcome used again? What do you mean by outcome? If you mean the accuracies or the reports from the validation sets, so the outcome of the evaluation is something we need to monitor. Okay, but if you are talking about the depth set itself, that depth set is being used again and again during the training. Okay. Not sure if that answered your question, but I'm going to proceed on to the next slide. Let me. So if I get you correctly, then probably the depth set is a holdout data set. That's never that is never used for training, but it's only used for the evaluation. Okay, so the gradients. So say we use mini-batch gradient descents. So the gradients will not be computed on top, out of the validation sets. Okay, so the validation set is not helping with the training at all. Training only depends on the training sets. All right, so one of the issue that we need to keep in mind is that in a design of modern machine learning or deep learning system, it is often a common case that the models are trained on different data sets, on different training data sets, but tested or the model we trained will be used on the different data sets. So for example, when a task is to do the image classification, we want to say that we want to train a model that tells whether it's salmon or sea bass. So it's easy to obtain training data sets. You can crawl millions of images from the web, okay? But in the case of testing sets, in the case where the model is being tested, or validated, the images can be from very different distribution. The images can be uploaded by users, so they can be quite different from the images, from the high quality images that the model has seen during training. Okay, so we basically use the principle that we need to be guided by the principle that when we train a model, we want to use some depth sets or validation sets that is similar to the final testing sets that the model is most likely to be applied to. Okay, so for example, in this example, in this development of the fish image classification. So when we train the model, it's okay, we use very high quality images for the training sets, but considering the users might upload very blur, low quality image, then we better use those blur or low quality images as the dev sets, because we don't know about the test. We only want to, what we can do is to use some low quality image to mimic or to simulate the probable user cases. Okay. Sometimes it's okay. So, but for example, we don't know about the actual what the actual testing case could be. So it's okay. We do not have an official test sets, but the result could be that we are using one dev sets, and so the models kind of is a overfit to the dev sets, right? Because we observe the performance based on the dev sets. So any model that is good, we claim to be good, is actually a relative concept that is based on our specific dev sets. Okay, so we'll come to the overfitting concept again in after we have talked about the performance metrics. All right, so for regression, for the performance metrics of regression model, using bad data. Yeah, so that is the, that is why we need machine learning. We need deep learnings and very complex models, because we want the model to be smart enough to deal with bad data. So if we are picky about the data, then why not we develop huge models to deal with complex cases, right? We want a model being trained from good data, well-labeled data, but again, we want the model to generalize well to unseen and maybe noisy, maybe irregular data sets, because that is kind of the whole point of machine learning or deep learning systems. We want the system to be intelligent, to be flexible, to be able to recognize the patterns that is disturbed by the unseen noises. Okay, so we want to be, we want to challenge the model a bit during the training, so that it's knows that, so it can deal with different situations with some flexibility. Okay. So let's talk about regression model, the performance. Actually, there's only one slide for this. In regression, we know that the label is a real number. It's a continuous number. And the testing set is also the same form, okay? So if we want to measure the performance on single example, a single point, we can simply use the distance between the predicted value and the actual value, right? So here, L1 error, we means the absolute value for the distances, okay? What we are more familiar with is the L2 error, because the mean square errors is the metric that we use in the training, right? So we can also use the same mean square error to do the evaluation on the unseen data sets, right? So we can use the distance and raise to the power of 2. So for the whole testing sets, we can use the average L1 or L2 error. And in the case of L2 error, it is simply the same thing as the mean square error. Okay. Or we can also use the standard deviation of the L1, L2 errors so that we can see how robust the model performed. Okay, so I'm not going to talk too much about the regression models because a regression model is kind of originates from statistics, and I think in statistics there are whole way more metrics talking about the statistical meanings of the coefficients, whether they are statistically reliable, the p-values. So not going to talk about those knowledge here, but the idea is that we can use the distance between the predicted value and the actual labels. So the focus will be the metrics for classification models. So in the simplest case, for binary classification, we have, for example, have trained a logistic regression model on that. And the model make predictions by first compute the linear combination between the data and the parameters W and V, and apply a sigmoid function on that, and use the outputs of the sigmoid function to indicate the probability of that data instance. Okay, so that is the meaning of the logistic regression model's prediction. All right. So we can pick a threshold, y hat equals 0.5 as a threshold. And for any prediction that has a probability that's greater than 0.5, then we say that the prediction is 1. In the other case, we say the prediction is 0. So the quantities here, they are all y hats. Okay, here's a threshold, and on the left is y hat equals 1. And we also see the colors, okay? The data points are different colors. So the color indicates the actual label of that data points, okay? So the green colored data points indicates the data points that are labeled as 1. And the gray ones are labeled as 0. So this is the so-called ground truth. Okay, so we notice that some gray data points are misclassified as 1. So that's where the model made a mistake. And one green point is also classified as 0. Okay, which is also an error or a mistake made by the model. Okay, so we basically want to use the relationship between the predictions y hat equals 1, y hat equals 0, and the actual labels to help us have an overall evaluation of the model. Okay, so the way we did that, the way we do that is to first draw something called a confusion matrix, or it's simply, you can think of it as a 2x2 table. Okay, it's nothing more than a table here actually. So it's a way to visualize the performance of a classification model. And what we can do is to place the actual labels into rows. Okay, so we place all the data points that are actually positive or labeled as 1 into the first row, and all the data points that are actually 0 in the second row. But in the setting, we also have 2 columns. So the first column is all the data points that are predicted as 0. Okay, and the second column are predicted as positive or 1. Okay, So in that way, we split all the data points into the 4 sections of the table or of the matrix, right? So we basically can count how many data points are in each section, right? So the number here, 12, means that there are 12 data points that are actually positive and are also predicted as positive, right? So it's basically the corrected prediction, right? And so is this section. So the 11 gray points here, they are actually negative, and they are also predicted as negatives, okay? But the section here, 1 and the 1 points, the 1 data point here and the 2 data points here, they are the misclassifications because the actual label for these 2 points is negative, but they are predicted as positive, right? The actual label for here, this one is positive, but misclassified as negative. Okay, so we give names to these numbers, and we use those values to come up with a basically a series of metrics. So first, true positive is the number here. Okay, and the name is also straightforward. It is the positive numbers that are correctly identified as positive. Okay, so we call it TP here. That's the number 12. And true negative, which is also straightforward. It is actually negative and predicted as negative, right? In this third section. So we have TP and TN now, all right? And next, false positive. It is indicated by the red number here. So it is the negative examples, but are incorrectly identified as yes, right? It's a kind of a false alarm, right? There's nothing happened, but the alarm says, okay, there's something happening. So that's the false alarm, okay? False positive here. And also false negative, okay? It is the yes examples, but are ignored or incorrectly identified as no, okay? So that's the name. We simply give names to the 4 sections, and there's meanings behind those names, which we will use in the next few slides to define a couple of more advanced metrics. Okay, so these TP, TN, FP, FN, these are the basics, bases for computing the next step. Okay. All right. So about false positive and false negative. At first, it might be a bit confusing, but I think it's easy to to understand if you are familiar with the cases, especially when you have a concrete example, right? And it's also equivalent to the concepts of type 1 error, which is false positive, and type 2 error that are people used a lot in statistics. Okay, so these are the meanings of it, but again, as I said, we will need to use all these 4 numbers to compute more advanced metrics here. So first of all, we talk a lot about accuracy, right? Accurate. We want the model to make accurate predictions. Okay, but a prediction can be positive and not negative. So we need to combine either way in the final computation of the accuracy. Okay, so we let the accuracy defined on top of these quantities. So we included, again, a new quantity called T, which is the total number of true data points, and the total number of negative data points, okay? And the accuracy is basically defined using these two sections, the true positive and the true negative. Because we want to know the proportion of accurate predictions made by the model. Okay, so, and we simply need to include all the correct predictions, okay, including the correct positive prediction and the correct negative predictions. And altogether, the accuracy is the fraction of correct predictions among all data examples. Okay, so that's accuracy. Okay, and of course, accuracy here doesn't distinguish the positive predictions and the negative predictions. Okay, so it is likely that the model is better in predicting positive predictions, right, as opposed to making correct negative predictions, right? It could be the case that the model is good at, making, is more likely to making positive predictions, but also it can, meanwhile, it also makes a lot of the false positive predictions. It raises the false alarms a lot. So if in that case, then we also need to think about whether this is the ideal model or not. Okay, so that's why we need a bunch more other metrics. So in this case, we introduced the metric called precision. Okay, so it's kind of considers the cases for false positives. Okay, so the precision is defined as the ratio of true positive, okay, among the total of true positive and for the false positives. Okay, so think of it that way. This model makes 12 plus 2 positive predictions in total. Then we want to see how much among these positive predictions they are precise. Okay, so that's where the name is from, precision. Okay, so it basically measures the quality of your positive predictions. Okay, so if your precision is low, then probably the model simply inclines to make more positive predictions. Okay, so we kind of want the precision to be high, right? Not just the accuracy. So that's our first index or first metric other than the accuracy. Okay, and we will have another one that deals with the false negative. Okay, so the false negative, again, false negative is those examples that are actually positive but are ignored by the model, right? It is not picked up by the model. So we define a concept called recall. Okay, so the recall is the ratio of true positives among the summation of true positive and false negatives. Okay, so it is actually the ratio of, or the fraction of correctly predicted examples among all positive ones. Okay, so if the recall is high, then only a little parts of the actual positive labels are ignored. Then we say that the model is pretty sensitive. Okay, nothing is left behind. And if the recall is not that high, then probably the model is too conservative, right? It is not bold enough to making positive predictions. So a lot of the actual positive cases are simply ignored. Okay, so that can be something we also want to ignore, right? That can be something we also want to solve, right? Because in different cases, sometimes we want to avoid the we want to as we want the model to be as sensitive as possible, and especially when it's dangerous, when there's a positive data point that is ignored or it is simply not picked up. Okay, so that's the definition of recall, right? So basically, for now, we have used the numbers here. For these three sections, we have used them to define precision and recall. And as a combination, well, let's first talk about this last section, which deals with the true negative and the false positive section. So it is the ratio of true negative among all negative numbers. Okay, so it's basically the proportion of actual negatives that are correctly identified as such case. So relatively speaking, this specificity or selectivity measurements is not used as often as the previous three cases, as accuracy, precision, or recall. Okay, and as I said, we will need a more balanced metric other than the accuracy, using the precision and the recall measures. So here we define the F1 score that combines the that uses both the false negative and the false positive, so that it combines the precision and recall. Okay, in a normalized way. Okay, so we simply use the products between precision and recall and times 2 and over divided by the summation of precision and recall. And that is a more balanced score because it considers both precision and recall. If either one among precision or recall is low, then the F1 score will not be that high. Okay, so this is a more comprehensive and it summarizes the overall performance better than the accuracy score. Okay, so it turns out that this F1 score or F measure is one of the most commonly used metrics when evaluating machine learning models. Okay, so that's the definition of the metrics by splitting the all the data points against their predictions, right? All the predictions are in the columns and all the actual labels are by rows. So that's the technique of coming up with the so-called confusion matrix. So this idea extends to multiple label predictions as well. So in that case, we can have multiple rows and multiple columns, right? But the concepts of true positive, true negative are gone because it is more than positive and negative labels. But again, these thoughts of dividing of visualizing data against using 2 dimensions, one is the true label, one is the predictions, is a pretty neat idea of the visualization. Okay, so one more advanced technique to measure the performance is to plot two curves, plot the curves that describes the relationships between recall and the false positive rates, right? Which is the false positive number of false positive against n. Okay, so that is a curve that we want to be as high, or if the curve has a larger area under it, then we say it's a better performance. Okay, because in ideal case, we want the model to be here. We want the model to have the highest recall, and it doesn't make any false positive. It doesn't make any false alarm at all. But that's purely in theory, and in practical, it's not. In practice, it's not likely to happen, because when the model try to make as much predictions as possible, right? It just inevitably making false positives, right? When the model is conservative, in order to reduce the false positive, then the recall is also likely to drop, because the model is hesitant to making positive predictions. Okay, so there's a balance, or there's a trade-off between the recall and the false positive rates. Okay, so we can use the ROC curve to visualize or to evaluate the model's performance. And within the ROC space, we want the models to be here or within this area. And the more it goes towards the bottom right, then these parts are worse areas, because the recall is lower than the false positive rates. All right, so that's one of the advanced technique. And if we extend to the multiple class classification task, we can simply extend the matrices. So from the table, we can see that which specific class works good, or which specific class is not as good, right? So for example, here the dog, 3 of the dog is classified as dog, right? But 2 of them is classified as cats, and 5 cat is correctly classified, but 3 of them is classified as dog. So it basically gives you a very quick way to spot where the model is good and where the model is not good at. And in computing the true positive rates, we can reduce the other categories into negative, right? So for example, if you actually want to compute the F1 score in the particular problem of cat versus non-cat prediction, we can simply combine the numbers, say, between dog and rabbit, and make them a one non-cat category. Okay, so that is some technical trick that we can use. Okay, so let's talk a bit about the trade-off between precision and recall. Again, we have mentioned that when we talk about the ROC curve, right? So the false positive rates is basically deal with the false positive number, and the precision is also a quantity that deal with the false positive. So if the model say, is conservative, then it is likely to have more false negative. Or in another way, it is more likely to have lower recall. If the model is bold in making positive predictions, then the precision is also likely to drop. Okay, so that depends on the question. Say, say in a police station, and if we use a criminal face detection technique to identify possible suspects, then I think it is okay that the model is bold in making positive predictions. Okay, because the worst outcome is that maybe the police will find the suspects and ask him questions. Okay, and that's basically higher the chance of getting the correct or finding the right criminal, with the cost of maybe sacrifice the freedom of some suspects, but that is basically the cost that we can afford, right? The force of a the cost of a false positive is not a serious cost. Okay, but maybe in the brain surgery, right? If we want to detect where there's a tumor in the brain to decide whether we need to conduct a surgery or not, then the false positive case is something that's really dangerous, right? We would rather the model to be conservative, because if it's a false alarm and we did the surgery, but turns out there's no tumor in it, then it's critical damage or critical loss that's already done and invertibly done. So yeah, so the trade-off between the precision and recall is actually a very practical question, a practical problem we need to consider case by case. All right. So lastly, we reached here overfitting parts, and the regularization technique to deal with the overfitting. So this concept it refers to the problem that the model's parameters fit the data too well, okay, and therefore they fail to fit new data, okay, or they fail to make reliable predictions, okay. And overfitted model, it basically do not find the general or stable patterns in data, but it is simply describing the very specific or very idiosyncrasies in the current data, but it doesn't tell a general pattern in general cases. Okay, so the cause could be that we use too many parameters and our training data is so small. There's not sufficient training data. Okay, so it's kind of a Occam's razors principle. Like if the less complex model can make pretty good empirical predictions, then we tend to use a simpler model. Okay, because the model is more likely to have more general predictions instead of making instead of capturing the idiosyncrasies in the data. Okay, so for example, in the regression model here, we have used this example before. If the model we fit is like this nonlinear regression model, we want to fit some quadratic line out of the data. So this line looks pretty good, right? Because it's kind of captures the general patterns in the data. And But what if we include higher order terms? We include a cubed and we include a um, um, x raised to power 4 something, then it may fit the data well. We may make the curve so that it goes through each data point exactly so that the loss is minimized. But it is kind of the overfitting problem we have, right? Because if we've got a new data point, right? If we've got a new data point here, right? If we've got a new data point here, then the model will not fits when the model will not go through the new data points here. I see a question that could another cause for overfitting be too many training iterations. Yes, exactly. Actually, that is another cause that can result in the overfitting. So one solution is that we do not train as many. We can set a threshold, or we let the model to stop early. So we let the iteration step to stop early, and that is the early stop technique. So we'll mention that a bit. Thank you for bringing that up. So overfitting, right? But using very little parameters can also, very small parameters or very few parameters is also a problem called underfitting, right? It is a obvious quadratic function pattern, but we ignore that and we simply use a linear function. That is something we also want to avoid. Okay, so it's a very, very subtle dynamic we want to reach, a balanced dynamic we want to reach. Okay, so yeah, in the case of classification models, it's even more visualized here. We want the boundary to be reasonable, right? Right, we want the boundary to be reasonable, so that's the boundary describes the general pattern, right? Instead of drawing some very specific boundaries that satisfies that tells each data point apart. That is something we don't want to see, basically. Okay, so now it comes to the problem of how to avoid overfitting. So of course, we can always use fewer parameters. Okay, and we can use feature selection to decide whether how many features we want to use. So I think we had a question in one of the office hour 2 weeks ago. So there's several ways of selecting features, right? We can start with the full feature and remove one by one and test the outcome of the model. Or we start from zero, a small feature, very few feature, and we add features one by one. Okay, and something called early stop. It deals with another cause for overfitting, right? We don't want to stop. We don't want to train a model so that the losses are squeezed to near zero, but that is not necessarily the best case, right? We want to evaluate on the depth sets and stop as soon as the performance drops. Okay, whenever the performance drops, it probably means that there's some overfitting detected by the validation data sets. And that is also a pretty common pattern in deep learning. Say we have a plot of losses. So the training loss, which I can draw in red color. So the red the training loss is always decreasing because we are fitting using the training data sets. And training loss is basically a metric out of the training data sets. But the validation loss or the depth loss is higher, usually higher, okay? And it doesn't decrease as fast as training loss, and maybe to a certain point it will flat. And if you go beyond this point, the validation loss could raise a bit ahead because there's some overfitting happening towards the training loss. So that's probably where we want to stop the training. Okay. So the technique that we focus on today is called the regularization term. And this is a very, very commonly used term. And nowadays in the mainstream machine learning frameworks, these are already built-in functions in the optimizers, okay? So the general principle is that we want to restrict the values or restrict the magnitude of parameters. We want the parameters to be not that big, to have not that big values, because higher values of parameters is an indicator of overfitting, okay? And the advantage of this third method using regularization is that no prior knowledge about feature is required. We just treat all features basically equally, and we just use some threshold to make sure that all the features, they are below some threshold in terms of their magnitudes. Okay, so the idea is that we modify the goal of the training a little bit. So in a typical gradient descent method, our goal is to minimize the cost function, right? We now change our goal from minimizing the cost function of the model with given the data. We now minimize the cost plus the complexity. Okay, so this complexity is a measurements of the magnitudes of the model, is a measurements of how big the parameters in the models are. Okay, so it can be quantified using the complexity term here. Can be quantified with a L2 regularization term. And an L2 regularization is simply the L2 norms of all the parameters. Say we have a vector W that has n components in it, and the L2 norms of this of all the parameters is simply W1 squared plus W2 squared plus Wn squared. Right? That's a very simple mathematical form, which is the L2 regularization term, and we include that term into the modified cost, okay, and modify the learning goal. Then this one, the direct result is that, sorry, the direct result is that we are minimizing the cost and the complexity. So we are actually minimizing the L2 norms of all the parameters. So we don't want the, in that way, we're limiting the magnitudes of all the L2 norms. We are making sure that they don't have overly large values. Okay. So in this concrete example of linear regression, the cost function. So here's a bit review. The cost function, now we write it in terms of W and B, but they are basically the same as θ1 and θ0, okay? So the cost function, original cost is the mean square error, right? And here's the regular L2 regularization term we include. We have this lambda, which is a hyperparameter, which is a constant that we use to control the strength of regularization. And this W transpose times W is the dot production, which is basically the same thing as the L2 norm. Okay, so with this modified cost function, we can basically change the form of the gradients, right? When we talk about the gradients of W, when we compute the gradients of W, the gradients of the cost with respect to W, it was previously only with this term, right? But now we include this term, and that is the gradient, that is the derivative of this second term with respect to W. So we have an extra term in the gradients. Okay, so now we need to use these new gradients in each step of the gradient descent, right? So we need to modify, we need to minus from W with the learning rate alpha times new gradients, and the results will be here, right? 1 minus alpha times lambda over n times W. Okay, so previously, without this L2 normalized L2 regularization, there will be no such a term. But here we have it, and as a result, the W will have smaller values, right? Larger lambda means larger penalty to W, because larger lambda means we minus a larger value from the previous one of the W, okay? And the larger lambda we have, then the smaller magnitudes of W's we will have. And the smaller magnitude of W means that less risks of overfitting to the training data set, okay? And same case to the logistic regression model. So in the logistic regression, the cost function like this, and we similarly, we add something as L2 regularization, okay? And we can also do the compute the gradients, and it's basically the same form as linear regression. So the new updates for W will have a smaller magnitudes decided by the lambda, controlled by the lambda. So lambda is something we predefined when we design a model. We need to consider how much regularization we want to place, so that's overfitting is avoided. Okay. So the outcome of the L2 regularization is that we have smaller parameters, and the model, a smaller parameter means that some say higher order terms, they have less, they have smaller coefficients, so the model is less complex, or the model is less nonlinear. So the decision boundaries is not that nonlinearly. So it is less likely to overfit. And when lambda extremely large, then that will result in the case of underfitting, because all the W's become very small. So the higher order terms, they don't matter at all. And if lambda is too low, right, the model will be more complex, right? So lambda is something we want to determine. Basically, it's an empirical process. It depends on how large the training data is. Okay, so Google provides a pretty good playground for L2 regularization and basically any other tricks in machine learning. I'm not sure if that link still works, but it shows some pretty nice animations of how the loss goes when you set a lambda or not, or when you set a large lambda versus a small lambda for L2 regularization. All right, so if you're interested, you can follow the link and to check out those animations yourself. So that's it for the content today. We basically talk about training, testing, validation, splits. We have come up with the performances for classification models, and we've talked about overfitting and especially the L2 regularization term. So I would like to make an announcement here, and this Friday morning from 10 to 10:45, I will give a seminar talk about a practical guide to PyTorch for machine learning beginners. So I think it'll be helpful for any one of you who are interested in using machine learning in your study or in your research tasks. I think it's PyTorch is a very flexible and also a very large software package that includes all kinds of toolkits, and it allows you a very large flexibility in terms of manipulating data and designing models, and the good ways to visualize, good ways to do research. So hope you can come. If you have time, you can jump in through the same Zoom ID, but with password PyTorch this Friday morning. And I also made an announcement about new office hour and the TA's office hour as well. Please check out the email, and the office hour on Monday will start next week. If you have any questions, you can let me know by now.
Hi, Professor.
Hi.
I have a question about the quiz that we have last week. The second question that it said that the cost function j theta is always greater or equal to 0. But as I know that the cost function is always the negative, right? So why the cost function is always greater than 0 is the correct answer.
The cost function is basically the negative of logarithm of a probability, right? So
yes, correct.
The logarithm of a probability is a negative number, and then you add a negative on top of that. So I think it's always
Oh, okay, yeah. Oh, that makes sense. Okay, yeah. So kind of like because the probability is always less than 1, so
yes,
the logarithm of that. Okay.
yes.
But what about the likelihood function? The likelihood function is always remained positive or greater than 0, right?
The likelihood is something you want to maximize. So the likelihood is something you don't have the negative. So it's always negative value.
Okay. Yeah, let me just double check with it to the formula thing. Thank you.
Right. I see a question that what is the difference between normalization and regularization? So normalization is I think it's a very general term that we use a lot, not just in machine learning, but in basically a lot of places when we deal with data, right? So in normalization, in data, given a data set, we normalize each feature, each column by subtracting from the mean value divided by the standard deviation. That's kind of a normalization, right? But the regularization term is basically the L2 regularization that we talk about when we design when we modify the loss or when we modify the cost function in order to gain less overfitting in training a model. Okay, so actually for normalization, we are not right. We are not referring to any specific technique about machine learning. But actually, later on, we're going to talk about something called batch normalization, and that is another thing that is totally different. But I think the term normalization is a broader term. Okay. The seminar, yes, I think I'm planning to record it and released. I will publish probably in my YouTube channel. And maybe I can, yeah, I can post, make a post into this Converse page so that people can see. Yeah, I think it's more related to our course. Okay. If we don't have questions, I will end here. And thank you for coming. And I will upload the video later this afternoon and release the quiz questions to Canvas too. And have a good day, bye.